We live in a universe of extremes, searing heat and bone-chilling cold. From the blazing heart of our sun to the frozen silence of intergalactic space, temperature is everywhere, shaping the very fabric of reality. Every moment we are surrounded by a delicate balance between warmth and chill, a cosmic dance that has been ongoing since the dawn of time. The warmth of a cup of tea or the sting of an ice cube are our daily encounters with temperature. These simple sensations connect us to the grander forces at play in the universe. The comfort of heat on a cold morning, or the shock of cold water on a summer day, are reminders that temperature is not just a number, it's an experience, a force that shapes our lives in subtle and profound ways. But Earth is mild compared to the cosmos. Our planet is a rare oasis where temperatures allow life to flourish. Yet even here we see wild swings, from scorching deserts to icy poles. In the vastness beyond, the extremes become almost unimaginable. The sun's core blazes at millions of degrees, a nuclear furnace that powers our solar system and bathes our world in light and warmth. Its surface is a roiling sea of plasma, constantly erupting with energy. Meanwhile, the void between galaxies is colder than anything we know, just a few degrees above absolute zero, where atoms barely move and time itself seems to slow. Temperature shapes everything. It decides if a planet can have water, drives the colossal storms that rage across Jupiter, and sculpts Saturn's rings from ice and dust. It determines whether worlds are barren or bursting with life, and whether atmospheres swirl or remain still. The universe is a tapestry woven from heat and cold, with every star, planet, and nebula telling a story of temperature's influence. From the fiery birth of stars to the icy silence of distant moons, heat and cold are the threads that connect everything. To truly understand it, we must ask, what is temperature? From supernovae outshining entire galaxies in a single cataclysmic moment, to the faint afterglow of the Big Bang that still lingers in the darkness, temperature is the key to unlocking the universe's secrets. In the stillness of deep space, where temperatures plummet to unimaginable lows, temperature defines existence itself. It sets the stage for the birth and death of stars, the formation of galaxies, and the evolution of everything we know. It's the engine of creation, fueling the birth of new stars and worlds, and driving the cycles of destruction and renewal that shape the cosmos. And it is the quiet of eternity, the cold silence that waits between the stars, reminding us of the universe's vastness and mystery. Exploring these extremes isn't just curiosity, it's a quest to decode the universe's fundamental rules. Scientists peer into the night sky, searching for clues in the heat of distant suns and the chill of cosmic voids, hoping to understand how temperature shapes everything from atoms to galaxies. The story of hot and cold is the story of the cosmos itself, a tale of energy, transformation, and the endless interplay between fire and ice that defines our universe. So what is temperature? It's a question that seems simple, but the answer takes us deep into the heart of physics and the nature of matter itself. We use thermometers every day, but what are they really measuring? Is temperature just a number, or is it something more fundamental? In physics, temperature isn't a substance you can touch or see. Instead, it's a measure of motion, a way to describe how much energy the tiny building blocks of everything around us possess. Everything in the universe, from the air we breathe to the water we drink, is made of atoms and molecules. These particles are always in motion, even in the coldest environments imaginable. Temperature quantifies the average energy of this microscopic chaos. The faster these particles move, the higher the temperature. The slower they move, the colder it feels. Imagine a busy city square. At high temperature, people rush around, bumping into each other, full of energy. At low temperature, they stroll slowly, barely interacting. This is a perfect analogy for how particles behave at different temperatures. When something is hot, its particles are zipping around at incredible speeds. When it's cold, those same particles slow down, moving sluggishly or even locking into place. Take water, for example. Heating it up makes its molecules move so fast that they eventually break free from the surface and escape as steam, turning from liquid to gas. Cooling water does the opposite. The molecules lose energy, slow down, and eventually arrange themselves into the rigid structure of ice. This transformation is all about the speed and energy of the particles. This idea forms the basis of the kinetic theory of gases, a cornerstone of modern physics. It helps us understand not just water, but all matter, from the air in a balloon to the metal in a bridge. That's why a balloon expands when it's warm. The air molecules inside are moving faster, pushing outward. And it's why heat always flows from hot to cold, as energetic particles transfer their energy to slower ones. The faster particles collide with slower ones, sharing their energy until everything reaches the same temperature. This process is happening all around us, all the time. This simple yet profound idea underpins countless phenomena, from the weather outside to the way your refrigerator works. Temperature is the language of energy in motion, a universal code that describes how matter behaves and interacts. It's how we make sense of the invisible world within everything, from the smallest cell to the largest star. By understanding temperature, we unlock the secrets of matter itself and begin to see the hidden dance of energy that shapes our universe. If temperature measures motion, what happens if you keep cooling something down? There's a limit, absolute zero, where classical particle motion stops. On the Celsius scale, that's minus 273.15 degrees. On the Kelvin scale, it's zero. Nothing can be colder. No motion means no lower temperature. But quantum mechanics says we can never reach perfect stillness. The Heisenberg uncertainty principle ensures a tiny, irreducible jitter, 0-point energy. So, absolute zero is a theoretical boundary, never fully attainable. Yet scientists can cool atoms to within a billionth of a degree of it. At these temperatures, matter behaves in profoundly strange quantum ways. The quest for absolute zero opens a window into the deepest mysteries of reality. Look up at the night sky and you're staring into a cold void. The universe's default temperature is about 2.7 Kelvin, just above absolute zero, thanks to the cosmic microwave background, the afterglow of the Big Bang. Any object far from stars will cool to this baseline. But some places get even colder. Deep inside dense molecular clouds, thick dust blocks out nearly all warmth, dropping temperatures to around 10 Kelvin. These are the coldest natural environments we know. Molecules barely move. Yet, the universe surprises us with even colder exceptions. The coldest known place isn't empty space or a dark cloud, it's a dying star's nebula, creating its own cosmic refrigerator. Here, the laws of physics push cold to the extreme. The Boomerang Nebula, located about 5,000 light-years from Earth in the constellation Centaurus, is a truly remarkable cosmic oddity. It holds the title of the coldest known natural place in the entire universe, a record that has fascinated astronomers and physicists alike for decades. At its heart lies a dying star, nearing the end of its life. As it runs out of fuel, the star sheds its outer layers in a spectacular display, creating a ghostly, expanding shroud of gas and dust that glows faintly against the darkness of space. What makes the Boomerang Nebula so extraordinary is its temperature. The gas here has been measured at just 1 Kelvin, only a single degree above absolute zero. That's even colder than the cosmic microwave background, the faint afterglow of the Big Bang that fills the universe at 2.7 Kelvin. This frigid environment is created by a process of rapid expansion. As the star ejects its gas at speeds of nearly 500,000 kilometers per hour, the material spreads out into the vacuum of space, cooling at an astonishing rate. The cooling is so efficient that the nebula's temperature drops below that of the surrounding universe itself. It's a rare example of nature outpacing even the coldest cosmic conditions. In a way, the Boomerang Nebula acts as a natural cosmic freezer, a fleeting laboratory where the laws of physics are pushed to their limits. Here, molecules and atoms behave in ways that are nearly impossible to replicate on Earth. This record-breaking cold won't last forever. As the nebula continues to expand and interact with its environment, it will eventually warm up, losing its title as the coldest place in the universe. But for now, the Boomerang Nebula stands as a stunning example of how the universe can surprise us, pushing the boundaries of what we thought possible in the race to the coldest. It's a testament to the ingenuity of nature and the fundamental laws that govern the cosmos. The nebula reminds us that even in the vast emptiness of space, extraordinary phenomena can emerge. The Boomerang Nebula challenges our understanding of temperature and physics, showing that even in the coldest corners of the universe, there are still mysteries waiting to be explored. Nature's coldest places are impressive, but humans have gone further. In labs, scientists cool tiny samples to temperatures far below anything found in space. Using laser and evaporative cooling, they slow atoms to a crawl, just millionths or even trillionths of a degree above absolute zero. Lasers break atoms, Evaporative cooling lets the hottest escape, leaving the coldest behind. The current record, 38 picokelvins, trillions of times colder than deep space. At these extremes, matter enters a new realm, ruled entirely by quantum mechanics. We're not just making things colder. We're exploring a world where the rules of reality change. The pursuit of cold is a journey to the edge of the possible. Here's a mind-bender. Scientists have created systems with negative Kelvin temperatures. Does this mean colder than absolute zero? Not exactly. Negative Kelvin isn't about less energy. It's about how energy is distributed. In a normal system, most particles are in low-energy states. At negative Kelvin, more particles occupy high-energy states, a population inversion. This is hotter than infinity on the temperature scale. Negative Kelvin systems will give up heat to any positive Kelvin system, no matter how hot. It's a strange artificial state, but it's real, and crucial to technologies like lasers. The temperature scale is more bizarre than it seems. Near absolute zero, matter transforms. Familiar states, solid, liquid, gas, give way to exotic quantum phases. The Bose-Einstein condensate, BC, is one. Atoms cooled so much that their quantum waves merge, behaving as a single superatom. In a BC, thousands of atoms act in perfect unison, a macroscopic quantum state. Another marvel, superfluidity. Liquid helium below 2 Kelvin flows without friction, climbing walls and never slowing down. These aren't just curiosities, they reveal the quantum rules underlying reality. In ultra-cold labs, we can observe quantum effects on a visible scale. Superfluids and BCs are windows into the quantum world, normally hidden by thermal noise. Extreme cold lets us hear the faint whispers of the universe's deepest laws. These states are gateways to understanding matter at its most fundamental. The quantum world comes alive in the cold. Why do we chase the cold? Because stripping away heat reveals the universe's true nature. Ultra-cold atoms power the world's most precise clocks, improving GPS and communications. Superfluids and superconductors promise efficient power and advanced technology. Studying extreme cold helps us model neutron stars and probe the mysteries of dark matter and energy. Each step closer to absolute zero opens new scientific frontiers. The pursuit is driven by curiosity, a desire to know the universe's rules. Ultra-cold physics is a new frontier, where matter behaves in ways we're only beginning to grasp. Every fraction of a degree colder brings us closer to the heart of reality.